All right. Welcome to the white paper series. The first paper that we're discussing today is Attention is All You Need, the paper that came in 2017. And yeah, so that has been a great paper of all time. Let me just open the paper. Yeah. So this is the original paper. I think it's available online. I will drop the link in the description. Now we're going to talk about the whole paper and what exactly has been described in the paper. So since we have read this paper a lot of times, we will cover its subsections in a different way. We will not go traditionally reading the paper line by line. So we have read the paper, we have extracted whatever is super important, and especially the stuff that is transferable and that is applicable to other architectures also. So we have extracted all of that stuff, and we have described it in some subsections, and we're going to discuss that, right? So let's see how this format works out, and let's also aim to absorb all the subsections of the paper through our own representation of it, right? Okay. So the first section that we will start with is, as the paper introduces, attention mechanism. The first thing that it introduces in the paper is the introduction section. The introduction section is all about why do we need attention? Why do we need to move beyond RNNs? So just imagine that we were in a deep learning journey where we had introduced recurrent neural networks. We had LSTMs and bi-LSTMs, right? So which were improvement over recurrent neural networks. So now this paper introduced the idea of attention. The paper kind of questioned why do we even need the idea of attention, right? So the first point, or the first problem that they mentioned with respect to RNNs and LSTMs is this: the idea of sequential processing, right? So we've seen that RNN is all about sequential processing. We process sequence 1, sequence 2, sequence 3, sequence 4, so on in a particular order, right? And we move in a direction. For example, let's say left to right. So each word is processed, each sequence is processed, let's say tth sequence is processed after t minus 1 is sequenced, right? So we move in incremental sequence windows. So this was one of the blocker. Why this was one of the blocker? Because there is very strict dependency and cascaded dependency, right? So you cannot unroll the dependency and parallelize it, right? It was very difficult algorithmically to parallelize it. So we wanted something which maybe can parallelized, right? So we will look at what exactly is going to be parallelized. So we can understand from this particular problem that whatever attention is going to bring, we don't know what it's going to bring, but definitely it's going to be parallel, right? Second thing was, long range dependencies were very hard to model, right? So it's like, cascaded forgetting, right? So if the information that was read in the earlier tokens of the sequence, and when as we move forward in the sequences, we used to forget what did we read, for example. And we introduced LSTMs just to conquer this particular idea, but still with LSTMs we were making this particular problems. So even with LSTMs, this path gets weaker over long distances. That's why it was very difficult to model long range dependencies, right? So we needed bigger sequences, bigger contexts, and bigger memory, right? So the keys which, for let's say this example, the keys which were lying on the kitchen counter this morning before I left for work and forgot to pick up are still there, right? So I mean, here the idea that keys and R, I mean, R is correlating or R is pointing to keys, is very difficult because there are 17 tokens, I mean, or more than 17 tokens, right? Depending on the tokenization algorithm between keys and R, right? So an RNN is expected to remember keys, through all of these 17 words to get R plural correct. I mean, basically, R should know that it's pointing to keys, right? Or the neural network should know that R here is pointing to keys. And between keys and R, there are significant amount of words, right? In this one particular long sentence. So this was also a challenge, right? So modeling language was not super trivial with recurrent neural networks. Why? The first thing was, computationally, it was sequential, right? We did not know how to parallelize it. So hardware was progressing parallelly, which is we were having advanced GPUs, but we want to leverage them. We want to leverage the matrix multiplication, of a parallel computer. We want the ability to parallelize the processing of all of these language modeling techniques. But since RNN was sequential, it was very difficult to leverage that hardware, so that was kind of a bottleneck. The second bottleneck is we need to model long range dependencies, right? So this was the second bottleneck. Now the third bottleneck is the weak gradient flow. So during the training time, gradients must propagate through every time step. So we know that in case of recurrent neural networks, we had a forward pass and we had a backward pass, right? So we used to call it back propagation through time, BPTT algorithm, right? It's very similar to gradient descent. So during the training time, gradients must propagate through every time step, and over long sequences these gradients either vanish or explode. We have seen that it was a very big problem, vanishing gradients or exploding gradients problem in case of recurrent neural network. This used to result in a very unstable training format, right? So this was also a very big challenge. So if you are very much clueless about all of these three parameters around RNN, all of these three challenges around RNN, then I think the best idea is to first go through recurrent neural networks. What is the architecture of recurrent neural networks, and how hidden state and output is being computed, the basic equations for the forward pass, and what is happening in BPTT, which is back propagation through time. So I think it's better to go through that particular topic first, in order to understand these three particular limitations of an RNN. Even if you don't know RNN and you still want to understand this paper, you can just try to absorb these three limitations of an RNN, and maybe read about RNNs after this particular video. So at least this video will help you understand the paper. Attention is all you need: self attention, multi-rate attention, cross attention, and then you can just go back to recurrent neural networks. Okay. Now, we needed some mechanism. We needed some mechanism that is more reliable, that at least solves this part, and it should also solve this part, and it should also solve this part, right? Okay. So the idea was, can we design a model that can capture sequence relationships or sequential relationships, since we were solving deep sequence modeling, without a recurrence or convolution? We had seen the idea of recurrence in recurrent neural network. We have seen the idea of convolution in convolutional neural networks. So these were the two mechanisms that we were very comfortable with, right? So we wanted to understand that there are limitations for both of these mechanisms. Can we have a different mechanism? So then the answer was, let's have self-attention as a different mechanism. So self-attention is nothing but, it gave us a formula, right? Now that formula helped us understand the contextual representation between two tokens, right? Now they said that, why don't you fill a whole matrix of all n square tokens, right? So that you can understand what exactly is going on between one token to the other token everywhere, right? So this was the answer: self attention. So what is self attention? We will introduce self attention very slowly, right? So we will understand the formula, we will understand what it's going to solve and how. So attention mechanism was introduced to solve all the problems that we were facing in deep sequence modeling with RNNs. So we had parallelization somehow, right? We will look at how. Then we had the ability to model long range dependencies. Then we had kind of stable training, because we kind of uh, solved the problem of vanishing gradients over long sequences, right? So now let's first see what exactly entails in the formula of self-attention. What exactly is the formula, right? So there are three components in attention, which is query, key, and value, right? We will understand what exactly are the three formulas. Now let's first see what exactly is the formula for attention. Yeah. So this is the formula that we introduced in case of self-attention, right? We will understand all of these subcomponents now slowly. So we can see that there is a dot product between Q and K, and then we're dividing it by a square root of dk, multiplying it and taking a softmax, and then again doing a product with value V matrix, right? So first thing is the terminology. Q stands for query, K stands for key, and V stands for value. Softmax we know is an activation function, right? This T stands for transpose, right? So we are doing this to make it compatible for matrix multiplication. Then it's a simple division operator, and we are dividing it by square root of dk. Dk is the model dimension, and V stands for value. There are three new terms that we introduced: query, key, and value. Now let's try to understand what exactly are these three ideas of query, key, and value. There are abstract ideas behind query, key, and value, right? And then there is a mathematical logic behind query, key, and value. Understand the mathematical logic behind query, key, and value, we simply should have a look at how tokenization gets done. So tokenization gets done on the whole language, right? So we get the we get the English like language text, and then a tokenization algorithm converts or breaks all of these sentences into a series of tokens. Each of these token gets assigned a token ID, right? So we can see that hello has a token ID, world has a token ID, and this particular token has a token ID, then this particular token has a token ID. So it also includes space, right? So this token is not only two, it also includes space. Then this particular token has a token ID, this particular token same, right? All, and this is a discrete token ID. This is not token embeddings. This does not represent the meaning of tokens, right? They are not token embeddings. Token IDs are completely different, right? Okay, awesome. Now just imagine that there is a series of matrix, right? So here the cat sat on the mat. Let's say this is a matrix here, right? On the right hand side here. Now I want to explain what exactly is query, key, and value, right? So let's imagine that these are on the vertical axis we have tokens ranging ranging on the iterator I, and on the horizontal axis we have tokens ranging on the iterator j, right? So each of the token I is querying or asking for the relationship, you know in each of the tokens in j, right? So the wants to establish a relationship with cat, the wants to establish a relationship with sat, and so on, right? So now what exactly we are saying, we are just asking that with respect to query, the abstract idea behind query is, what am I looking for in all of the tokens j, right? Or let's say out of all of these tokens in token j, what am I looking for? Key simply says, what do I contain, right? That other people might be looking for, right? Value is, what is the content, right? So it's very similar to how we visualize in case of a database. We have the concept of query, we have the concept of key, we have the concept of value in databases, in hash maps, in hash tables, and in a lot of other scenarios. For example, if you want to visualize, you can visualize Google search also. Let's try to see query, key, value with respect to Google search. Let's see how they correlate. Yeah. So if we see the analogy, what exactly is query? This is your search term or request, like the text you type into a Google search bar. It represents what you're looking for. Key. These are the metadata, the titles or the description associated with each item in the DB. Then value, this is the actual content or information, right? So the same mechanism is basically correlated. The same mechanism of query, key, and value is correlated with the Google search. We can also do with YouTube. Yep. What are you currently searching for? Your search query, for example, cats playing piano, right? This is your search query. This is the query matrix. Then key, you have an idea of key. So every video that we have in the YouTube database will have some key associated with it. Then obviously the video is going to have its own content, right? So query, key, and value, all of these three ideas are abstract here, but they kind of can be understood with respect to databases, with respect to Google search, YouTube search, right? Okay. Now mathematically, query, key, and value are nothing but three matrices, right? So if we try to visualize on this, the cat sat on the mat. Let's say these are uh, three simple matrices, right? We will see how they get computed, right? So when we want to understand how they get computed, we need to understand the idea of WQ, WK, and WV, right? So we now have fair bit of idea of what is query, key, and value. Now we are going to look at, how do you compute query, how do you compute key matrix, how do you compute value matrix, right? So we have WQ, WK, WE. So each of these WQ, WK, and WE are weight matrices. right? They get multiplied with x. Now what the hell is x? X is nothing but input embeddings, right? So whatever language that you were looking at, for example, this was the language that we were looking at, this got converted into tokens. Every token has a token ID. Now it's not enough. This is not the input to transformer, right? This is not the input to your attention sublayer. The input to your attention sublayer is token embeddings, right? So there has to this particular algorithm, after this particular algorithm, we have to undergo a process of converting, or let's say introducing token embeddings, right? So X is nothing but the input embeddings. Now what exactly is input embeddings here? Input embeddings is the combination of token embeddings and positional embeddings or positional encodings, right? So we have introduced a new idea here, which is positional embeddings or positional encodings. We always knew what are token embeddings, right? So think of token embeddings as we are trying to represent hello, hello, this particular token in a decay dimensional universe. Now let's say decay is, for example, here decay, just imagine that decay is 1 2 3 4 5 6 7 8 8 dimensions, right? So we are trying to represent decay. For example, here we're trying to represent the as a 8 dimension vector, and here we are going to represent decay, sorry, hello, as a 8 dimension vector. That's it. That is token embeddings, right? So the idea of token embedding is that it's going to explain the meaning behind the token. The idea of positional embedding, in case of RNNs, we did not have an idea of positional embeddings because we were processing sequence 1, sequence 2, sequence 3 in a sequential order, right? So we had relative positions or the understanding of relative positions. Here we don't have, natively we don't have a relative understanding of positions or understanding of relative positions. So what we introduced one more vector. One is token embedding vector. We introduce one more vector, which is positional embedding vector. Now this positional embedding vector is also decay dimension. Let's say here in case of, in this case, positional embedding is also going to be a 8 dimension vector. Now this encoding vector represents the position of the particular token. That's it. And adding both of them, doing a linear operation on these two matrices, gives us something known as input embeddings, right? So now what we do here is we take this input embeddings, multiply it with WQ, multiply it with WK, multiply it with WV, and then we get the idea of, or the mathematical formula, which is query, which is Q, then K, then V, right, value. Now, how do we compute attention scores? Attention score is the scaled dot product between query and key, right? So we multiply the query and key matrices, right? We take the dot product. Why dot product? Because contextual representation, we want to compute contextual representation between SAT and MAT, right? So the idea between contextual representation is that if we take a dot product gives us an intuition of similarity. That's how we measure relevance and similarity between two tokens, right? If the dot product is very high in magnitude, what that means is it's more, the two tokens are more similar in context. They are more relevant in context. If the dot product is 0, that means the two tokens might be orthogonal to each other. They are meaningless. They have no correlation, no relevance, no similarity among them, right? And negative, that means they're opposite, right? So this is the idea of taking a dot product. Now we have to scale them down. So that's why we call it scaled dot product. So why do we divide it by decay? Because the dot products can go very arbitrarily large, right? Dot products is nothing but multiplying two vectors. Let's say vector 1 and vector 2 getting multiplied, and then taking a summation of all the elements, right? So it's going to get too large. So we want to normalize, right? And we want to stabilize and normalize. So we want to bring them down. That's why we scale the scores by the dimension decay. Then we apply softmax, right? So the softmax on the scaled score converts all of these scores. The raw scores gets converted into probability mass, right? Now, why probability mass? Because we will be able to make that judgment, right? For example, here the judgment is, let's say if I'm standing at SAT, SAT is going to make a judgment for all the tokens in my vicinity that are in the token J set, which token has the highest probability mass, so that I can attend to it, right? So that's why converting everything into probability mass makes a lot of sense using softmax. and we use softmax. We don't use sigmoid here, right? One more uh, good idea behind softmax is that the summation of all the probabilities is going to be 1, right? That's why we can call it as a probability mass, right? So that's why we don't use sigmoid. Now, what we multiply it with value, right? So the attention weight that we have computed so far, it tells us how much to take from each token, right? The value vector contains what actually to take, right? So this is the combination that produces some context aware representation that, that is the most important part of the transformer, right? So scale dot product between query and k, and then scale it down by dk, apply softmax, and then multiply it with values. This is the 4-5 step process of computing attention. Very simple, right? And what is the input? The input here is x. What is wq? Wq, wk, and wv are the weight matrices. When we say weight matrices, then we simply mean that they are learned, right? They are going to be the few matrices that are going to be learned over time. They might be random in the start, right? In the initial times, they might start randomly, but over time, we're going to learn them, right? So far, we have seen the flow of information from all the language that was there in a text file. We converted or we tokenized them, produced discrete tokens. Then we converted or introduced token embeddings. Then we also introduced positional embeddings. After positional embeddings, we compute or we feed these particular embeddings to attention sublayer. Now, attention sublayer is going to compute attention formula. It's going to build attention matrix. How is this attention matrix going to look like? For example, the query matrix for the cat sat on the mat looks like this, the key matrix looks like this, the value matrix looks like this. All of these matrices are identical in sizes. That's why we are able to do the dot products very seamlessly. Then the attention matrix is going to be of order of n square, we can see, right? So all the tokens on the left hand side or on the horizontal axis and vertical axis are establishing a relationship among themselves, right? So that's why it's an n square matrix. So for every pair of token I comma j, we have our attention score, right? So it's pretty straightforward. Now the idea is multi-head attention. Why do we have multi-head attention? We have seen the self attention, but why multi-head attention? Okay, let's focus on why multi-head attention, then we will cater to more and more use cases. Yes. So in this subsection, I think we have described why do we need multiple heads. So I think we have discussed in deep learning talks also why do we need multiple heads. But let's again go through this particular idea. So we know in deep learning we want to understand two keywords, deeper and hierarchical, right? We want to model deeper and hierarchical relationship in the language. We want to, for example, if we are understanding images, we want to understand deeper and hierarchical features among all the images or all the image patches, right? So here also we need multiple heads. Why multiple heads? Because one single head can learn one type of attention pattern. If I have 8 such heads, I will be able to learn 8 such patterns, right? So that's why we need multiple heads. For example, if we talk about in abstract terms, we can learn the relationship of subjects to noun in one head, then nouns to verb, then noun is to adjective in different heads. So multiple heads can help us understand more deeper and hierarchical relationship between our language that we are trying to model, right? So that's why we need multiple heads, right? So what really happens is mathematically, let's say our dk or our single head was 512 dimension, or the total dimension of the whole model is 512. If we are using 8 heads, so one head is going to cost us 512 divided by 8, right, which is 64 dimension. 64 dimension for head 1, 64 dimension output of head 2, 64 dimension of output of head 3, and then we concatenate all such 8 heads to produce the 512 dimension meaningful embeddings, right? Okay, so this is basically what happens in case of multiple heads, right? Now let's keep on answering the questions as we go. Now the first idea is, why do we also need softmax in case of attention, right? So this is also a sub question that is underlying in the paper. So we need softmax because it converts all of the row scores of attention into probability mass, and all the values are going to be between 0 and 1, and they exactly sum to 1, right? So this is the main reason that we choose softmax over a sigmoid, right? Now, if we can see that if we are using softmax, we can see the probability mass, and all of the probability mass for this particular context window sums up to 1. If we had sigmoid would also convert everything to probability mass, and we could take an argmax, but it could not sum up to 1, right? So that's why sigmoid softmax works a little better. Now, uh, we also have to understand the idea of masking. So masking is in the idea, masking is lying or prevalent in decoders, right? It's not present in encoders, but it's very much prevalent in decoders. So let's also understand the idea of masking. So now we have understood self attention, multi-head attention, and the formula of attention. It's good that we understand masking so that we can jump on the encoder stack and the decoder stack. Okay, so what exactly is masking? We try to mask or block the future tokens. If I'm standing here, right, I can see everything till this particular token. If I'm standing here at cat, I can see everything till cat and before cat. For every token I, we are able to see token ranging from 0 so on till I, right? We cannot see I plus 1, right? So that's why we can see all of these tokens, and all the tokens that come after this. Let's say this is our I, this is where we are sitting. So we will not be able to see cat sat on mat, right? And if we are standing at cat, we will not be able to see sat on mat. And why do we mask them? We intentionally mark them as negative infinity. So if you apply softmax on this negative infinity, it's going to result into 0. Why do we mask them? We mask them because this idea of masking or causal masking is used in decoders. We want to teach the decoder only models to predict the next word. If they keep on seeing the next token, right? If we are standing at I and they're able to see I plus 1 token, they will not be able to enforce the behavior of predicting the next token. It's going to be called as cheating, right? So the model will be able to cheat and develop an opinion on of what is going to come next. But if we mask them, then the model is going to be forced to predict the next token, and then we can evaluate its prediction, right? So the causal masking or look ahead masking marks all of these upper triangular matrix into negative infinity. So if you're standing at cat can only see the token cat and the tokens previous to it, but not the future tokens. So the future tokens are masked, previous tokens are seeable, right? So it's unidirectional. We only go in one direction. So as we are moving ahead, we are unlocking more and more tokens, right? So we don't have the global or bi-directional visibility of all tokens, right? Okay, so it's used in decoder only models. We know that. It prevents the token from attending to future tokens. It ensures that the model can only use the past and current context. I think it makes a lot of sense. Why do we need it? Because at inference time, there are two phases, right? At inference time, future tokens are not available. So we want to make sure that at training time also future tokens are not available, right? Inference means the querying time. When we are querying, we want the GPT family or the decoder only models to predict the next token because it's not available. So similarly, what we're trying to do at the training time also, we only show model with masked sentences. Masking is forcing the model to predict based on only what has come before, right? The probability of token xt plus 1 given token x1, x2, x3, so on till xt, right? This is what we're trying to do, right? Okay, now we've seen multi-head attention, self-attention, masking. Let's go to the decoder and encoder stack. That is like the super important part of this particular paper. Yes. So here we have the decoder and encoder stack. Okay. Now let us look at what is happening, right? Let's look at the architecture. So we have input sequences, then we converted these input sequences into tokens, and then we have token embeddings, we have positional embeddings, then we added both of them. This becomes our input to the whole encoder. Right? The first thing that we see is an encoder. Encoder has a couple of sublayers. Let's see what are sublayers are there in the encoder stack. One is the multi-head self-attention, right? So we compute self-attention formula and we do it at multiple heads. So we have, let's say, 8 heads here: h0, h1, h2, h3, so on till h8, right? After that, we do this operation known as residual plus layer norm. Now, what exactly is this operation? This operation basically signals that you, uh, so the previous sublayer produced an output f of x, right? So you add the input to this output. So the input was x, the output was f of x. So you add x plus f of x. This is basically adding the residual. Then normalization. So then it instructs you to perform scaling and shifting operations for stabilizing the training and normalizing everything, right? So now there comes the feed forward neural network. So after this attention block and the residual and layer normalization operation, we have something known as feed forward neural network. We have seen the feed forward neural network, right? So after feed forward neural network, we will again perform the operation. So the only thing that we have heard very much new in this paper, uh, is the multi-head self-attention, which we went into detail, and the residual operation and the layer normalization operation, right? Feed forward neural network is super, I mean, it's very old to us. It's a simple neural network. We are stacking the neural network layers that are taking the, output of attention block, and then they're trying to produce deeper representation, or then they have their own hidden layers. So this is nothing but the whole encoder stack. Now we have a decoder stack. What exactly goes in decoder stack? So since we have decoder stack, we will know that in case of attention, the attention matrix is going to be order of n square definitely, but it is going to have masking enabled, right? So that's why we have masked multi-head self-attention. Here we have simple multi-head self-attention. What that means is, if we are dealing with an encoder, we don't do masking. If we are dealing with a decoder, we do masking. One good example of encoder only transformer is nothing but BERT. One good example of decoder only transformer is the GPT family, right? So the BERT family is encoder only, the GPT family is decoder only. And what family are we studying right now? So this is the machine translation family, which is the paper attention is all you need. So it has encoder and decoder both, right? So we have an idea of encoder stack where we have no masking. We have an idea of a similar decoder stack where we have masking, right? So we have multi-head masked self-attention. We have the same residual and layer normalization operation. We have cross attention. Okay, this is a new word. What is cross attention? Okay, I think we have discussed this also in greater detail in deep learning talks. So the cross attention is not same as self attention, right? Here the input is coming from encoder, right? In case of self attention, the input was coming from the input itself, right? Here we are taking everything from the encoder. So encoder is passing on whatever information it has learned to the decoder using this cross attention mechanism, right? So the formula is going to be same. I mean, the formula is going to remain the same. There are no major differences. The only difference is the source of input, right? So all the information is coming from the encoder instead of coming directly from the input, right? Then we perform the residual and layer normalization. Then we do feed forward neural network, and then again we do residual and layer normalization. So residual plus layer norm is being done after every sublayer, right? So the idea of doing this is constant in encoder and in decoder both. Then we have the output head, right? So the linear projection, the linear layers, and then we apply a softmax on it, right? So I think these are simple linear layer neurons, and then you apply softmax to produce probabilities, so that we can do the modeling. We can take argmax, or we can sample from the probability distribution that is produced from this output head and softmax, right? So we converted it into the French. So we started with English language, hello world, or hello, then hello is converted into bonjour, right? So this is the idea of encoder and decoder stack. Now we can dive a little deeper in both of the encoder and decoder, just to get more and more familiar, so that whenever we encounter the encoder stack in the future and the decoder stack in the future, we know what's going to happen in it. So now we've seen three formats of a transformer: decoder only transformer, encoder only transformer, encoder decoder transformer, right? So if you understand encoder decoder, we will be able to understand decoder only and encoder only very easily, right? So in this paper, the architecture that has been mentioned, there are six identical layers of encoder stacked on top of each other, right? Each layer has two main sublayers. We have seen that: multi-head self-attention and feed-forward neural network, right? So both of these are something which is crucial to encoder. Apart from this, we only have residual and layer normalization. So what exactly happens? we encounter input, right? So input is nothing but token embeddings, position embeddings, summation of both. Token embeddings, let's say it is 1000 cross decay dimension. This is also 1000 cross decay dimension. So we can simple do an element wise addition of these two matrices, right? This becomes the input, right? Now it goes to the multi-head self-attention sublayer, and we compute all the 8 heads of attention, right? So we compute the query, key, value, and the attention matrix, right? So we have something which is known as the attention output, so which comes out from this multi-head self-attention. So there's one more thing I think that is worth covering here. H0 came up with its own matrix in multi-head attention. H1 came up with its own matrix. H2 came up with its own matrix. H5 and H8, so on. I mean, all of these heads came up with their own matrices. We concatenate them, right? After concatenating them, just like we multiplied Q with WQ, K with WK, the V with WV, we multiplied the concatenated attention output with WO, which is nothing but projection matrix, right? Let me see if I have mentioned projection, idea of projection matrix here. Yes, I think yes, I have. Yeah. So WQ, WK, WV. Obviously, we compute self-attention, and what projection matrix is, you concatenate all the heads and multiply it with WO. WO is a projection matrix. This is also a learned projection matrix. Okay. Now let's get back to the encoder decoder stacks. Yeah. Okay. So we have multi-head attention, the attention output. Then, so you see, X was the input to this sublayer. This is f of x. This is the output of this sublayer. We add both of them, right? So now this has become the new input to the next sublayer, right? So then we normalize, right? We perform layer normalization. We perform the scaling and shifting operations to normalize this particular output, right? So what exactly did we do? We computed something. We computed some output from this sublayer. We added the input again, right? So that we don't forget more and more information, right? For more relevance and for more importance and for not forgetting, we did this particular operation, right? And this for the, we did this particular operation to stabilize the training flow, right? Then we compute the feed forward neural network, or then we have a feed forward neural network, right? Then we do the feed forward pass of the feed forward neural network. We have two linear transformation layers, and we are doing ReLU activation in both of these layers. And so we don't have softmax, we have ReLU here. So they will take in the input, which is this, and they will produce in the output, which is this, right? So they take in the feed forward neural network dimension, which was 2048, and they produce an output which is 512, right? So now this particular output, again, let's call it the normalized output, is going to be added in the output of this particular sublayer, right? So again, x plus f of x, right? So this residual operation is very standard. So you always remember it as if we are doing x plus f of x. That's it. Input plus output. That's it. Input of that particular sublayer added with the output of that particular sublayer. That's it. Then we are doing layer normalization again. So in case of this paper, which is attention is all you need, we call it the post layer normalization paper. In the GPT family, the normalization is proposed before every sublayer. Here we have proposed after every sublayer, right? So that's why that is pre-layer normalization. This is post-layer normalization. This is also one more difference between both of these papers. Okay, so now we have something which is known as the output. Output again belongs to the set of real numbers of dimension, sequence length into D model. So D model, you can see that we have always been consistent with D model, right? And this pattern repeats 6 times in this particular paper. In this particular architecture, we have 6 encoder stacks, right? With each layer refining the representations further, the output of the final encoder layer is being used by the decoder, definitely, right? So we stack all of these layers. Now let's also understand decoder, right? Okay, in case of decoder, what we have is um all of the same sublayers apart from this particular one, which is multi-head self-attention. We simply do mask self-attention, right? So what exactly is happening here? The decoder also has 6 identical layers stacked on top of each other. Each layer has 3 main sublayers, right? So it decoder takes input y also belongs to the set of real numbers. So it is of dimension target length into D model. So the input is similarly computed from token embeddings and positional encodings. we do masking here, right? So the masking that we use is causal masking. Masking only happens at the attention sublayer, right? It does not happen at any other sublayer, because while we produce the attention matrix, we want to mask or hide the future tokens. That's it, right? So causal masking is ensuring that position I can only attend to positions less than equal to I, preventing the model from cheating by looking at the future, right? Then again we do the layer normalization. We can see that layer normalization is again, so y was the input to the sublayer, so y, which is the input, then output was nothing but the output of the sublayer. So we do input plus output, right? Input of the sublayer, output of the sublayer, x plus f of x. Very similar mental model to remember residual operation. And layer normalization is again performing a normalization layer. So you can, if you have heard normalization before, if you have not heard about normalization before, you can simply look at this formula, right? So this is very standard formula for normalizing, which is z-score normalization. So which is nothing but x minus mu divided by sigma, right? So we have different normalization techniques. We're not going to go into greater detail, but just to get started, you can understand z-score normalization, min-max normalization, and other different normalization techniques, so that it does not intimidate you, right? And then you can read about layer normalization, scaling and shifting vectors that are used to normalize. So, okay, then we have something which is known as encoder-decoder cross-attention. So here the query input is coming from, y, the key is coming from the encoder output, right? So the encoder, which was stacked on top of decoder, is sending us encoder output for key and encoder output for value. Only the query is something that we use from this particular stack, right? So this is the idea of cross attention. The formula of attention remains the same. We call it cross attention because we are passing information from encoder to decoder. Decoder is querying, decoder queries q attend to encoder keys and values, right? So this is where decoder sees the source information that encoder had seen. Each decoder position can attend to all encoder position, right? So what that means is we get all the source of information from encoder in the key matrix and in the value matrix, and our decoder positions can attend to all the encoder positions, right? So the only difference between here this particular attention and this particular attention is, which is self attention, is that here the source belongs to this particular sublayer, but here the source is coming from encoder stack. That's it, right? Okay. Then we again have a feed forward neural network. So all the same sublayers. So we are computing multi-head self attention, we are computing cross attention, then we are doing feed forward neural network, and that's it. So this operation is constant. We have seen this a couple of times. It is after every sublayer, right? So feed forward neural network again converts, uses ReLU and uses, its hidden layers, and there are two hidden layers that it uses, and it computes it feed forward pass, and then obviously it will also have its backward pass. So after the feed forward neural network produces output, we again do residual and layer normalization. Then we will have an output, right? Now this output belongs to the set of real numbers of size, target length into D model, right? D model again is constant here. Okay. So after all the 6 decoder layers, we have produced logits, which is probabilities, right? Now we use the probability of next word. We applied the softmax, or the softmax function as part of the output head on these logits, so that from this particular softmax we can use the probabilities to sample the next word, right? And we can also do autoregressive generation in case we want to simulate what a decoder does, right? Okay. Now I think we've understood most of the subsections, right, of the paper. We've understood the attention mechanism, we've understood multi-head attention, self-attention, cross-attention, encoder stack, decoder stack, encoder decoder stacked together, causal masking, and the breakdown of the attention formula. Why did we want something like attention? Why do we want softmax? Why do we want cross attention? Why decoder uses masking? Right. So all of these questions we have tried to answer. Now, what the only thing that we want to conclude is Why attention improves transformers? Why do transformers use a mechanism like attention? We have seen that we are able to model long range dependencies. We can have bigger and bigger context windows. We are not dependent on one particular sequence, then another sequence, then another sequence, and we are not processing like that. We have global contextual relationship between all token i's and token j's, right? Then we have parallel processing. All the heads can go get computed parallelly, right? Similarly, attention is basically parallelizable, right? We are not having strict tightly coupled dependencies, at every particular sequence. So sequence I is not tightly coupled and tightly dependent on sequence I minus 1. So we don't have that concept here. All the positions are processed simultaneously or parallelly, making the training much faster than sequential RNNs, right? So I think these are the two problems that we saw in this case, that why we cannot, so why RNNs were failing short. Yeah, so these were the two bigger problems that we had. And one more problem that we saw in case of RNN was the gradient flow. Here we have residual and layer normalization to stabilize the gradient flow, right, or to stabilize the whole training methodology, right? So I think, yeah, it's pretty straightforward. Now the Oh, okay. One idea that we have failed to cover is positional embeddings. Let's also cover the idea of positional embedding. So what kind of positional embeddings are used here? Okay. So we saw that we have certain token IDs, and now these token IDs are converted into discrete. So these text is going to convert it into discrete tokens, and discrete tokens to discrete token IDs. Then we have token embeddings, right? So let's say embedding of this particular token 14, embedding of token 982, embedding of token 4501, right? So we call them x1, x2, x3. Now we add something known as p1. We had an e vector, we have a p vector, which is positional embeddings. Now positional embeddings are nothing but vectors representing the position of this particular token, the relative position of this particular token. One simple idea could have been to use discrete token IDs, maybe a sequence counter. But obviously that's not possible, because we are dealing in a continuous space. We are not dealing with discrete space, and our neural network that we are using, or the transformer, does not know how to do subtraction and addition to compute relative position. For example, if I do discrete token IDs, let's say on the cat sat on the mat. So if the has 0 as its position, this has 1, and this has 2, this has 3, I cannot know if on comes after the, right? I will have to do a negative or subtraction operation to compute the relative position of on with respect to the, right? So that's a little unrealistic. So we wanted a continuous space, right, and to represent positional embeddings. So we use sinusoidal waves to model positional embeddings, right? So we use cos and sine functions to model positional embeddings in this particular case, right? So all of these token embeddings are static. Oh, sorry, all of these positional embeddings are static. They are not trainable, right? In case of GPT family, we don't use this, right? We use simple weight matrices for positional embeddings and learn them over time during the training phase, right? So this is the idea of positional embeddings, right? So I think now we have mostly covered all of the areas of this particular paper. Attention is all you need, and we also understand the pipeline of computing attention. Uh, Token IDs, token IDs to token embeddings, token embeddings to positional embeddings. We add both of them. It goes to the multi-head attention sublayer. We compute all the multiple heads. We combine them and then multiply it with projection matrix. Then it goes to feed-forward neural network. So one more question: what are the trainable parameters? I think this is going to be the last question that we answer for this particular paper. What are the trainable parameters in this particular attention based transformer? So the trainable parameters are obviously all the weight matrices around WQ, WK, WE, right? Then output projection matrix. So once we compute all the multiple heads of attention, we concatenate them, we multiply it with WO. So this is also a trainable parameter, right? Then token embeddings. Token embeddings are also trainable. We don't use static token embeddings. We don't use a word to vec embedding model to convert and freeze the embeddings. So the embeddings are learned over time, right? Positional embeddings. In case of the GPT family, we have positional embeddings also as trainable. Here we are using sinusoidal waves or simple sine or cosine formulas. So here we are using these formulas to simulate positions of ith position and I press 1th position, right? But there we don't use that. In case of GPT family, we make positional embeddings also as learnable vectors. Then feed forward neural network weights, obviously, all the feed forward neural network sublayers are also learnable. Then layer normalization parameters. So the scaling and shifting vectors that might be used in case of normalization are also trainable, right? Okay, so I think all of the subsections are decently covered, and I hope this was very much helpful. I can attach the original paper. So the idea of producing this visuals was to not get intimidated by the paper and cover it subsection by subsection, right? So we will keep on experimenting, and we will keep on noting down what all strategies work the best, and use that particular strategy for the papers, right? So uh, but I hope this information was pretty useful. I can attach the link of the paper and the link of the visuals that we made to understand the paper. Thank you very much for tuning into the white paper series. I will see you in the next video.